Okay, last lecture. Last lecture on random graphs, last lecture in this course. Graph minors, the highlight of all of it, unfortunately happens in graph theory 2 only, but it'll be full of it. So come back then. Today is the last lecture on random graphs, and let me start by a reminder of the curiosities that we saw last time. We had lots of statements saying for all probabilities p in the interval, open interval between 0 and 1, the following things are true. Things that we don't really want to be true all the time, like almost every graph is 1 million connected, and so on. But apart from that, the choice of p didn't matter. So there's clearly something wrong there. And there are two things wrong. One is that constant p is too large. As we saw in the proof of R.Diestel's theorem, p there, the critical p was 1 over n. So the probability with which an individual edge is chosen, independently for all the edges, depends on the space that we're in, and the space is always tailor-made for one n for one number of vertices on which we choose those edges. So we want p to be allowed to depend on n, and then we can ask whether we have phenomena, as in the proof of R.Diestel's theorem, that at some particular function of n, something switches. So let me define that. T as in threshold, right? T, function of n, is a threshold function for the graph property G, or no, let me call it P, so as not to confuse it with G and P, if the probability that G, and G is in G and P, as always. The probability that G has this property tends to, well, to 0 if the probability P grows more slowly than the threshold, or decays faster than the threshold. I always speak about growth, even though 1 over n isn't really growing very fast, right? So decays faster is the same as grows more slowly. And if the probability grows faster than t, or decays less fast than t does, then the probability that G has this property should tend to 1. Okay? So the probability that G has this property should tend to 0 if P divided by T tends to 0. So if P grows less fast than T, and if it grows faster than t, then it should go to 1. Okay? And brackets, this quotient will be abbreviated to gamma, just because gamma is so much less to write than this. Okay, right. So that is going to be the definition of a threshold function. And we'll compute threshold functions for the following property P. Compute this. I shall propose a certain function, claim it's going to be the threshold, and then prove that it is, for pH, where H is a concrete graph, a concrete abstract graph, not a particular graph on the vertices between 0 and n-1, but an abstract graph. So pH is the property that G contains H. Abstract is a little sort of dubious wording, right? What I mean is H is some graph, and pH is the property that G has in a subgraph that's isomorphic to this H. Okay. In particular, we'll show that a threshold function exists. It's not obvious. In fact, threshold functions don't exist always. There are properties you can write down, you can construct properties, slightly artificial properties, for which there is no threshold function. You can prove that. Unfortunately, you didn't get the exercise to do that, but it's a fun exercise. Anyway, so they do exist for most natural properties. In fact, there's a theorem by Bollebash and Thomason, Andrew Thomason, Baylor, Bollebash, and Andrew Thomason, 1989 or something, who proved that with some very few exceptions, every increasing property has a threshold function, where a property is increasing if adding edges to your graph that has the property maintains the property. Okay, so threshold functions do tend to exist in cases that interest us. So how should we do that? How should we find such a T? How should we prove that if somebody whispers a conjecture T into our ear, how should we go about proving that it is the right one? Well, there are two parts to that proof. Right, we'll have to show that for gamma going to 0, so for the probability growing less fast than the threshold, almost no G in GNP has our property. And for P growing faster, we'll have to show that almost every G in GNP has the property. Sorry, I hope I said that right last time round. So for slow growing P, we want almost no graph to have the property. For fast growing P, we want almost every graph to have this property. Okay, and these are two rather different things to prove, and the methods also differ a lot. First trick is to rewrite P as in terms of a random variable being positive. So rather than showing that H exists in G, we'll define X as the random variable that counts the copies of H in G. Okay? So that's x of g. Right, a random variable on g, function of all the g's. Just the number of copies of h in g. So, and then p of ph is just equivalent to saying that x is bigger than 0, that there exists a copy of h in g. And that's good news. Why? Because we have some tools about bounding the probability that this happens, especially from above. So there's Markov. Remember Markov's inequality tells us that the probability of x, and let me write x is at least 1, which is the same as a very, very important trick today, as x is bigger than 0. Sometimes I need this, sometimes I need that, but of course they're the same because x is integral. So the values of x are natural numbers. Okay, so the probability that x is at least 1 is bounded above by the expectation of x divided by 1. Right? That's Markov. And so in order to show that the probability that G has a property goes to 0 for certain gamma, we'll have to show that this value goes to 0 for certain gamma. We'll just show that this value goes to 0 for certain gamma. Right, so that'll be easy. How about the other half? How do we show that if the probability grows faster than t, or decays less fast than t, that almost every graph has that property? So translated in this way, we want to have a lower bound. We want to show that the probability that x is positive, strictly positive, is at least something. How do we do that? Expectation again? Let's think. Suppose we know the expected value of x. What can we deduce about the probability that the measure of the subset of all those g where x is at least 1? So we know the mean, we know the expected value, we know the integral of x. And we want the probability, the measure of those g where x is non-zero. We want that to be large. What assumptions about the expectation will allow us to deduce that? Answer, none. Example. So I have have our graphs here, G and P, all these graphs, right, the random graphs, elements of G and P, and we have X there, and we want the measure of the graphs where X is positive to be large. Okay, so here's my favorite X. Not my favorite X at all. So I'll be a spoil sport, right? I'll make X 0 everywhere. Well, I can't make 0 everywhere, or else my expectation would be large, which I'm trying to test whether assuming large expectation is good. So here, I'll make X really big. And then it's 0 again. So no, that's not what I want. I want the other one. So I want the measure of those G where X is positive to be large, but it's small. All right? Even if the expectation is large. So mu is an abbreviation for the expectation of X. Did we have that last time? Can't remember. So little box, expectation of X is always abbreviated to mu. This is a little misleading if you're not used to it, because that looks like a constant, looks like a number. No, it's not a number. Well, of course it is a number once everything is fixed, but once X is fixed and also N is fixed. Right, but it depends on N. Okay, so bounding this probability below by the expectation is not a good idea. Okay, so how can we change this for the better? We need that our random variable is not as erratic as this one. So we need, and this is now, I write this in words because it's so important, X deviates from its own mean, its own average value. Rarely a lot. Right? So unlike here X deviates everywhere where this yellow area indicates that X is 0. Everywhere where X is 0 deviates a lot from the mean because we made the mean big. So, for example, well, not for example, but it should look more like this. Should more like this. So we have X is non-negative, so something like that. Then the mean is maybe here. Right, so it's sort of about the average of x, which just dips to 0 briefly there. And we can see that it differs, x is 0 here, and it differs from its mean a lot here. But that happens rarely, because blue is taken. Okay, so rarely this has small measure. And then we're in business. Why? Because 1 is somewhere here. All we want is that x is bigger than 1, and we want the measure of that happening to be large. Right? So we want, that used to be yellow here. No, but okay, it's better like this. So we want this large, right? The measure of those g where x is bigger than 1, or is bigger than 0, is at least 1. And we get that by saying, well, yes, it's certainly at least 1 whenever x deviates only a little bit from its own mean, assuming the mean is positive. So the deviation from the mean is small enough here to keep this, although it dips below the mean, it doesn't dip below the mean too much, not so as to go below 1. Here it does go below 1. All right, so this is fine, and x is indeed at least 1 there. Right, so that's what we want, and of course I'm probably preaching to the converted. You've all seen Chebychev's inequality, and that's it. I think who has taken the probability course? Oh, overwhelming. Come on, you can own up to it. Yeah, okay, just a handful. Fine. Okay. Right, okay, then but I promise you to go through all the basics here anyway, so that's part of the basics, but that's fine. Okay, so Chebychev's inequality. That is 1141. Chebychev's inequality says that, I'll start with, okay. So it says that the probability that x differs from its mean, as we discussed here, a lot, where a lot my abbreviation for a lot is at least lambda. Lambda is going to be some number later. Right, so the probability that this is at least lambda, which I want to rewrite in a slightly different way, and this just measures the difference, right? So if I want to square that. So x minus mu squared is at least lambda squared. Just same thing, just squared, right? This is positive, so that's the same thing. And that is bounded above by Markov's inequality, by the expectation of this, right. Do you need two brackets? No. Expectations of this divided by lambda squared. Okay, and that gets an abbreviation too. This term here is called sigma squared, the variance. Let me just write that more explicitly. Sigma squared is defined as the expectation of x minus mu squared. Yeah. Okay. Right. Now this let's just work it out. Right? Let's just do the square. So that's the expectation of x squared minus 2 mu x plus mu squared. And now, the expectation being an integral is linear. So that's expectation of x squared minus, let me write it, minus 2 mu expectation of x plus mu squared. But this here is mu. So we have minus 2 mu squared plus mu squared. So that is the same as e of x squared minus mu squared. So when you see that in the literature, you just see this is the definition of sigma squared of the variance, and then it's defined as that, and then they say it's equal to that, and you say, hey, what? Can one do that with squares? And of course you can't, normally, right? So don't think you're going insane. You're not. It's just because of that coincidence there. Okay, I thought I'd spell that out for you. I got stuck there when I first saw it. Yeah. Okay, so what's our approach? Our approach is that we want to assume for a proof of this that x doesn't deviate a lot from its own mean. Otherwise, we can't prove very much. So, for case gamma goes to 1, that's the second case here. What's that? Infinity. Huh? Oh. Thank you for nearly telling me earlier. Okay. So, brilliant. All right. For that case, we'll assume that this goes to 0 for the largest lambda that we can afford to use. We want this. We want that the probability goes to 1 if gamma goes to infinity. We shall be assuming this, because otherwise we don't have a chance. So we'll be assuming that this goes to 0 for some suitable lambda, right? So that the probability that x deviates a lot from mu, which is the bad case, that goes to 0, so that for the rest, where it doesn't deviate a lot, we're in business, right? So which is the largest lambda for which that works? So which is the largest lambda for which, assuming that this goes to 0, implies that this goes to infinity? This measure really is big. Well, we want this deviation here to be bounded by exactly mu, right? So this x, we want to stop x from deviating from its mean by as much as mu. That's enough. If it deviates less, or for many g with large measure, deviates less than mu, lambda equals mu, then for everywhere where it deviates less from its mean than by mu, this x is going to be positive, trivially, right? So we'll assume that this goes to 0 for lambda equals mu. Thank you. Any other occurrences? I'll probably do it again. And, yeah, the lag time is coming down, so that's a good sign. Okay. Right. Questions up to here. I've just outlined the approach that we'll be taking. I haven't started the proof. I haven't started finding t. Fine. Okay, questions? Good. I'm just summarizing what we've done. If, mu has to be bigger than 0, obviously, and sigma squared divided by mu squared goes to 0 for n to infinity. For all n large enough is enough. Right? Everything is always done for n large enough. Okay. Here it's written there explicitly. Then almost every g has our properties, so let me write it in terms of x. Right. Then x is going to be positive, strictly positive, in our application, at least one, there will be a copy of H in G for almost every G. Okay. So that's 11.4.2. Maybe a quick word about this. So is mu going to be positive? Yeah. X is positive. X is non-negative. So mu cannot be negative. Mu can be 0, but only if X is identically 0, which is not going to be the case. Right, so that's always the case. Of course, the smaller mu, in principle, if we're not integral, if X is not integral, this mu is allowed to be tiny. It can even tend to 0 itself. Right? It should be above 0. It needn't be bounded away from 0 as n grows. But it should be above 0 for all n large enough. And then we just require that sigma squared decays more quickly than mu squared. Right, so that we can do that trick up there. Okay. So basically, I just want to assure you that assuming that mu is bigger than 0 is not going to be an issue. So in applications, if we want to prove this, which is our second case up there, the case of gamma going to infinity, it'll be enough to check that. Right? I won't be talking about the property itself anymore later. I'll just talk about checking that for our concrete application. Okay, so let's get going. Now, find threshold for our particular P. Find the threshold T for our particular P, and H, let's fix some parameters for H, so give them names. Let's say H has k vertices and L edges, and X counts the copies of H here. That's the X we'll be talking about. And gamma I defined, so that's all I want. Right. Okay, so let's do the easy case first, where gamma goes to 0. So we want few copies of H in G. Right, we want the measure of all those G that do contain a copy of H, where X is positive, to go to 0. Okay. So let's give the potential copies of H in G a name. Let's call that curly h. Curly h is the number of all, sorry, the set of all copies of h on the right set of vertices. Namely those vertices on which our G and P lives, or G and GNP lives. All right? Okay, that's our curly h. And so in order to prove that the expected value of x is small, which is what we want, let's count the size of these copies, so of the potential copies. Let's just see how many there are. Well, how do you get a copy on the right set of vertices? This is a set of n vertices. So we first have to choose the vertices of the h prime that we want. And how many are there? K. So we need to choose k vertices out of our n vertices to start with, to pick one copy, one element of curly h. And on each fixed set of k vertices, we can have several little h primes. So let h denote the number of copies of h on a fixed k set. So if our little h is a complete kk, then there's only one. Right, but if it's a more complicated graph, then there can be several ways of putting that on there. So if the graph has many automorphisms, this little h has many automorphisms, then little h is going to be small. Right? Anyway, so the only important thing is that this is going to be less than, at most, k factorial. K factorial is sort of the various ways one can pick k vertices. So it's an upper bound for the number of h's on a particular k set. Right, and what's that? So this is n factorial divided by k factorial, which cancels this, times n minus k factorial. So that's n factorial over n minus k factorial. So that's n times n minus 1 times and so on, all the way down to n minus k plus 1. Right, so this is k factors left, which are all at most n. So this is at most n to the k, which is all we're going to use. So this is going to be at most n to the k. Okay. Right. So let's compute this. I think I'll do one big line. So the probability of h being at least 1, which is what we want to bound above. We want that to be small. right? Where in the case that gamma goes to 0, we want almost no g to have a copy of h. So we want the measure of those g's that do have a copy of h to be small, to go to 0. So let's bound that above. That's the expectation of x being at least 1 divided by 1. So this is Markov. Okay, so what's this? That's the sum of all over all possible h's, right? The okay. Yeah, so this, okay. So what's that? The expectation of x is the sum, remember this matrix that we had where we computed the expectation for this particular random variable? We for every little h, for every candidate on the right vertex set that might or might not be in h, we put a row, and then we just added the measure of those g that contain that particular h. And we summed that over all the rows. So we want the probability that this particular h is in G. Now, what's that? H has L edges. So we need these L edges to be there, so we have P to the L there. Sorry. This is for, yeah, for one summand, so P to the L, and of course how many summands are there? Well, at most that many. I'm now using that. N to the k times P to the L. Okay, and let me just rewrite this P in a slightly different way, namely as gamma times T. So that's N to the k times gamma to the L times T to the L. Why am I doing that? Because we're assuming that gamma goes to 0. So gamma to the L is going to go to 0. So we want N to the k times T to the L to be at most 1. Okay, so, I mean, N to the k just looks pretty big, but then, I mean, we can make T small. Right. So, let us simply define T so that it works, so that T of N to be, now let me get that right, N to the minus K over L right? So if t is this, then t to the L is going to be n to the minus k times n to the k is going to be 1. Right. Let me just give this a slightly different wording. Oops. N to the minus 1 over epsilon of h. Right, remember epsilon? Number of edges divided by number of vertices. So L over K. We have K over L here. So that's 1 over epsilon and a minus in front. That's nearly our pitch for T. Right, so that's sort of naively the best we can do. In fact, it's not quite good enough, but nearly. So we'll get to the real T just in a moment. Okay, now let's do the other case. Case 2. Gamma is going to infinity. Okay, and now we want to apply Chebychev and so on. But no, we don't. We just want to verify this. And then we know by all that we've done in preparation that it's going to work. Okay, and we'll do that for a slightly larger t. So there'll be a gap between the t that we'll be working with and this t that we have done in the first case, and we'll have to close that gap. And the way we'll be closing the gap is that we'll replace this by the slightly larger one that we'll get now, but that'll be really easy. So let me just define that t of n be 1 over, n to the minus 1 over epsilon prime of h where epsilon prime is the largest density, largest epsilon that occurs in a subgraph of H. Oops. No. 1 dash is enough. The largest epsilon of H prime, so that H prime is a subgraph of RH. Right, so the edges might not be completely uniformly distributed over H, or uniformly is a technical word I shouldn't be using that. H need not be balanced in the sense that it can have some subgraphs that have a bigger epsilon and others that have a smaller epsilon. We take the biggest. So that's going to be epsilon prime of H. Okay, so why can we work with this revised T? So this T is a little bigger. Epsilon prime is a little bigger than epsilon. Right, but because we're taking this maximum, so this gets bigger, so 1 over this gets smaller, so minus 1 over this gets bigger. So T is going to be a little bigger. So for the second case, where we want T to be big, P to be big, we'll start at a slightly higher level and prove that for p bigger than the slightly bigger t, the second case works, but we've only shown that for p up to a smaller t, the first case works. So there's a gap there, but the gap isn't important because the first case also works for this revised t. Now, why is that? The first case says that almost no G has a copy of H for this particular probability being below the threshold. But then it can't, but if we adjust the threshold to the densest H prime in H, that'll be enough to show that those almost all G don't contain a copy of H prime, because then they can't contain a copy of H either, because H would contain this H prime. Right, so it's fine. We can replace this epsilon here with epsilon prime, so that'll be fine. But for the second case, we really do need epsilon prime, and I'll show you in a moment where. Okay. So, have to show for all epsilon bigger than 0, no matter how small, and all n large enough, we have the following. We want that sigma squared divided by mu squared is less than epsilon, right? We want this to go to 0. And that's just the analysis one version of writing that something goes to 0 by saying for every epsilon it has to be smaller, right, for n large. Okay, so we want this to be less than epsilon, but I want to rephrase that as follows, using this funny trick here, that. So I want to rephrase that as E of x squared divided by mu squared to be at most 1 plus epsilon. Oh, sorry, this epsilon, of course, isn't that epsilon. That's an analysis epsilon. Okay, so why this? So sigma squared is that, the expectation of x of the function x minus mu in brackets squared. But that happens to be the same as expectation of x squared minus mu squared. Right, expectation of x squared minus mu squared divided by mu squared. What's that? That's expectation of x squared divided by mu squared minus mu squared divided by mu squared. That's minus 1. And that should be less than epsilon. So shift the 1 to the other side, and then we'll have that. Okay. Right, so I need my notes for such deep things as this. I should have used my notes for the infinity up there earlier as well. Right. Okay, so that's what we want. Have to show, precisely. We have to show this. And we'll do that by rewriting x squared in a really funny, creative way. Rewrite x squared as, what is x squared? X is, maybe I should write of G. So x squared of G is x of G squared. What is x of G? That's the number of copies of H in G. So how do I want to write that? Yeah, just like that. Okay. Oops. That's the number of copies H prime in G of H squared. Okay, fair enough. And that we shall rewrite as as the number of pairs H prime, H double prime in H squared such that H prime and H double prime are both in G. Right? So it looks like a stupid way of rewriting that. We count the number of H's in G, square that number. We may as well count all the pairs where each of the items in the pair satisfies exactly that. So H prime and H double prime are allowed to be identical. Right, so you have a set A with 17 elements. How do you count them? What's the square of that? Well, you take 17 squared. But you can also count the number of pairs in this set because that happens to be the square of the cardinality of that set. And why is that, not entirely stupid? Because we can look at how H and H prime lie with respect to each other inside G, and there'll be a huge difference there. The expectation of x squared and I'm using this phrasing for x squared now, is simply the sum over all the rows. There's one row corresponding to every pair. The probability that H and H prime and H double prime are both in G. Right? So we have a set of elements of these pairs. It's it's more a cube than a square now, this matrix, but for every pair we have a row, and the event that corresponds to that row is that both H and H prime are in G. Or in other words, that the union is in G. And then for that row, we take the measure of the G's that satisfy that contain both H and H prime. And we do that for every pair H prime, H double prime. And we sum over all these pairs here, we sum over those measures of the G that satisfy that. And that's going to be the expectation of x squared because of this silly rewriting. Okay. And this sum, we're going to split into different sums depending on how much H and H prime intersect. But maybe I don't want to do that just yet. Just see. Let's just give them names. A0 plus A1 plus AK, where AI is this relevant sum with H and H prime meeting in exactly I vertices. So sum over those pairs H and H prime that meet in exactly I vertices. Right? So that can take a value anything between 0 and k. We just want to do these sums separately because it will make a difference what I is. Questions up to here? Right. Then for I equals 0, we get lots and lots of possibilities of having H prime and H double prime because they don't have to meet. So think of G being huge, and we want two little k-sets, here and there, or here and there, or here and there, or here and there. Lots and lots of pairs of k-sets. If they're disjoint, there'll be lots of sets. If they're not disjoint, then for every, there's lots of ways of choosing the first, but once you have the first, the second one has to dock onto this. So there'll be far fewer choices when I is between 1 and k. And that will make a big difference. So let's just do this for I equals 0. Yeah, well, we have I0 being the sum. I'll just put some index 0 here for this I of precisely that. So I'm just copying this now, that H and H prime are both in G and they don't intersect. But that is simply, so if they don't intersect, then of course this happens independently. So the probability that they're both there is the product of the two probabilities. So that's P of H prime in G times the P of H double prime in G. All right. Now let's drop this restriction that we're summing over 0, sum over all pairs H h double prime in h squared. And let me just copy that. P of h in G and P double H in G, right? We're just, previously we were assuming that we're talking about disjoint vertex sets. Right, now we're adding some nonsense. So we're certainly not going to be smaller, that's all I'm saying. Right, we don't want to analyze what we're adding. We're just adding some nonsense, thereby we're not going to be smaller. But this is easier to compute because that is just, here we're summing over these squares, and this has nothing to do with h double prime, and this has nothing to do with h prime. So that is sum over all h prime in h curly h p of h prime in G, times the same for h double prime. Okay, so what's that? What's this? What's this first factor? Well, think of the original matrix. For every h prime, we have a row. And we're summing the measure of those G that contain this particular h prime. And now we're summing all those over all those rows. Ever done that before? No? Yes? That's the expectation. Right? That's the expectation of a copy of H being in G. So that's mu squared. Mu for this and mu for that. Okay, so we've used up our allowance almost entirely. All right, so we want the sum. Where is it? The sum, here. This sum here, the expectation of h squared is this sum. The expectation of h squared divided by mu squared should be at most 1 plus a little bit. So a naught alone divided by mu squared is going to be 1. So the rest divided by m squared is going to be less than a little bit. It will have to be less than a little bit, but it is. Okay. So let's do the rest. All the other AI are tiny because there are fewer pairs. Right? As I said previously, once you fix one copy of H, the other one has to start with at least one vertex, so that that's already a restriction. That's strong enough to make all these AI smaller than their share of epsilon, so smaller than epsilon divided by k, if you like. So then, and these dots are for a lot of computation, which you can read up in the book if you're so inclined. Then the overall, expectation of x squared, which is what we wanted to compute. right, which is the sum of those of A naught and the other A's, AI, is at most mu squared. This mu squared is the bound for that, plus epsilon mu squared for all the others. Hence, epsilon of x squared, expectation of x squared divided by mu squared, and is going to be at most 1 plus epsilon, and that's what we needed to show. That's that up there, right? Okay. So, questions about the proof? Okay, you can read it in the book. Don't get bogged down too much by the inequalities. Try to see what's happening. Yes, I share your smile. Yeah, I can't even distinguish one from infinity. So, okay. Let me summarize this by stating the theorem. This is Addish and Rainey in combination with Bolabash later for the epsilon prime. And it says that if H has at least one edge, then T of n defined as that, n to the minus 1 divided by epsilon prime of H is a threshold function. For pH. Right? Okay. So, corollaries. What if H is a cycle? What's epsilon prime? One. Right? Number of edges equals the number of vertices, and in every subgraph, we even have more vertices than edges, so the maximum of epsilons is for the cycle itself, so epsilon prime and epsilon are both 1. So what happens here is n to the minus 1. Cool. Remember I said that when we proved Addish, that when we're lower than n minus 1, we not only don't have any short cycles, we have no cycles at all. Right? For any fixed length, we almost surely have no cycles of that length. But one can even prove that we almost surely have no cycles at all, which is a slightly stronger statement. Okay, next corollary, trees. Any tree so T is n to the minus k divided by k minus 1. Right, minus, of course. So a tree has epsilon. Well, it has one more vertices than edges, right? So 1 over epsilon is the number of vertices divided by the number of edges, which is that. Okay. So are you ready for the final big picture in 2 more minutes? Let me shift that out of the way. So the final grand picture is sometimes called the evolution of random graphs. I mean, this is an ancient term, Edith Rainey, 1960s, I think, when random graphs were born. So evolution of random graphs. What does it mean? It means that we look at probabilities P of n and let that grow with n. Consider faster and faster growing functions or less and less fast decaying functions. And then we'll encounter thresholds. And I'm going to tell you the thresholds. So when p is less than n squared, so t is my, if t is n squared, t of n is n squared, really tiny, then this is our random graph, and I'm going to draw what almost every random graphs with this number of edges looks like. Yes. Okay? So that's p less than n squared. Now, if p is a little bigger, so say n squared less than p less than root n times n squared, right? Then the components are single edges or single vertices. Yeah, I won't write the text down because we're out of time. So let me just like that. So the components are k1s and k2s. Now, next step up. Root n squared less than p less than 1 over n, so n to the minus 1. Components are trees. Okay. So we don't have any cycles yet because we're below n to the minus 1. We're below 1 over n. But the cycles are coming now. So n to the minus 1 less than p less than log n times n to the minus 1. Oh, I shouldn't be using yellow. Oh, shucks. So, orange. Then we have some cycles. And later, as we're approaching this, they'll coalesce more and more until there's only one component that swallows up everything else. So this is called the giant component that devours all the other components as the probability approaches this. Okay, when we've passed that, then the feast is complete. The giant component has eaten everything else. Yeah, let me just write this now. G is connected. Okay, and now as a little fun addendum at the end, if we're just a tiny bit bigger than what is needed to make G connected, so if we have 1 plus epsilon times that, log n to the minus 1, then not only is G connected, but it has a Hamilton cycle. Remember how difficult it was to force a Hamilton cycle? You need a min degree of more than half the vertices, something huge. Yeah, so that ends my overview of the beginnings of random graph theory. Any questions?
You meant n to the negative 2, right? Because n squared will be much larger than 1.
Sorry, I meant?
You wrote n squared, but n squared is larger than 1.
N squared?
Yeah.
I didn't. Oh! Yes, thank you. You want a yellow minus. No, and a white minus. Thank you. Yeah. Any other little remarks? Huh? Anything else?